Our last section about factoring techniques. What we're going to do in the next section is just talk about, in general, if I give you a polynomial, how do you factor it? And then the section after that is going to talk about how do we solve equations now using this factoring process. So really we're just going to go over special forms of factoring. So if you have some key features, what do you do? And honestly, the same stuff from the last section is going to apply. Still, you're going to make your first terms multiplied to the squared term, your last terms multiplied to whatever the last term is, and then you're checking the outer and inner add up to what you want. But in this case, we're going to have very special first and last terms. And so this is going to be an indication to just try one of these specific forms. So we're going to go through three. We're going to go through the difference of squares. So you have one square term minus another. We're going to go through perfect squares, and then we're going to talk about perfect cubes. And so the first two things, the squares and the perfect square trinomial, those are still going to fit into this guess and check process, but because the first and last terms are perfect squares, you have an indication as what probably a good first guess would be. The cubes is the thing that's going to stand out on its own, and unfortunately that is the memorization for the formula, but there is some similarities between them, so it's nice in that sense. So we're going to start with our difference of squares, and we're going to begin by first multiplying out an expression that looks identical, but the signs are going to be different. So if we multiply these out, we get a times a for the first term, which is a squared. The outer term is minus ab. The inner term is plus ab. And then the last term is a minus b squared. So what ends up happening is the outer and inner are exactly the same thing, but they're opposite in sign. So those actually will cancel each other out. And that leaves us with a squared minus b squared. Okay? So this is exactly what our difference of squares is. If we notice that we only have two terms and they're both perfect squares, it'll factor nicely into a plus b times a minus b. So let's try a bunch of examples. We're going to start with x squared minus 16. And I'm going to recognize this is something squared, this is something squared, and I have no middle term. So I may be able to memorize this formula and memorize what it is going to factor into, but I'm really going to think of it just as make the first terms multiply to the x squared, the last term multiply to the 16, and then I'm going to check, do my outer and inner give me nothing that's in the middle. So to get to x squared, my only possibility is x times x. To get to negative 16, because it's a perfect square, I'm going to try positive 4, and I'm going to try negative 4. And so if we do the same thing as last time, this gives us negative 4x for the outer term, positive 4x for the inner. They add together and give us 0x. So the middle term cancels out. Okay, so this is our right factoring. And the reason we're going to know that is because we have x squared minus 16. They are perfect squares. So it's x squared minus 4 squared, which factors into this x plus 4, x minus 4. So anytime your first and last terms or the constants in front of them are perfect squares, try that number. So that's going to be your best first guess. So like in this next example, 4r squared you can think of as 2r squared, and 9 squared is 3 squared. So the front and last are perfect squares. So let's try 2r and 2r, and let's try a positive 3 and a negative 3. So that's my good guess to make the first and last terms line up. If I check the outer, it's minus 6r. The inner is plus 6r. That indeed cancels out and gives us no middle term. So that is our correct factoring. Okay. So for these other ones, I'm still going to just do this guess and check process. But using the fact that 25 and 9 are perfect squares, I'm going to go ahead and use that as my guess. So to get to 25m squared, we can do 5m and 5m. To get to this last spot of negative 49, we can do negative 7 and positive 7. And then we have p squared, so let's put a p and a p. If we check the outer term, that's negative 35 mp. And if we check the inner term, it's 35 mp. So the outer and inner cancel and give us nothing in the middle, which again, what we want. Okay. For this next one, we have a couple options. Since we do want to factor it completely, my gut's telling me I have a 4 and I have a 64. They're both divisible by 2 at least. Really, the biggest number I can take out is 4. So I'm going to start by factoring that out. That will leave us with a squared. 64 divided by 4 will give us 16. And so this again left me with an expression with 2 terms. A squared's a perfect square, 16's a perfect square. And I have no middle term, so my best guess is to put an A and an A, a 4 and a 4, make one positive and make one negative. And again, if I check, this is negative 4A, this is positive 4A, that adds up to my missing middle of 0A. Okay. If you didn't notice that, that's perfectly okay. Maybe instead you noticed that both of these numbers were perfect squares. So instead, I went right into guessing of 2A and 2A, and 64 being 8 and 8. And then I make one positive and one negative to get that negative sign. From here, this would give us negative 16A, and the inner is positive 16A. So that is the correct factoring. But I still have stuff in common. So from the first piece, they both have a 2 that we can take out. And from the second piece, we can also take a 2 out. So that leaves us with 2 times a plus 4. Take out another 2, and we're left with a minus 4. And then one last step of condensing the 2 times 2, it leaves us with 4 times a plus 4, a minus 4. So we still end up with exactly the same thing. It just took us a little bit longer to get there. So let's do one more example. We've got x to the 4th minus 81. So I'm going to set up my parentheses again. 81 is a perfect square. So let's do a 9 and a 9. Make one positive, one negative. X to the 4th, we can say that's x squared times x squared. Okay. Now the problem is I still end up with something that has this form where I've got perfect square minus a perfect square. Unfortunately for this one, I can't factor it more. So what you might try to do is you might set this up, okay? It's x squared plus 9. I'll try an x and an x. It's positive 9, so we do a 3 and a 3. But unfortunately, this gives us plus 3x plus 3x. Doesn't give us no middle term. So this isn't the right factoring. But I could try negative 3 and negative 3 as well, and it still does the same thing. That gives us minus 3x minus 3x. Doesn't add up to the no middle term here. So when you have a perfect square plus a perfect square, it unfortunately isn't going to factor more. It's this minus that makes it possible because the outer and inner will cancel. So really from here, we can keep going. This is x squared plus 9, and that will factor into x plus 3 times x minus 3. Because the inner will be positive 3x, and the outer is negative 3x to cancel and leave you just with the x squared minus 9. So this is something you have to be really careful about. If you have x squared plus 9, it does not factor into x plus 3 times x plus 3. Nor does it factor into x minus 3 times x minus 3. You unfortunately are not able to factor it anymore at all. So So this leads us into our next topic, which is a perfect square trinomial. So same kind of idea. The first term's a perfect square, last term's a perfect square. Now we're going to have a middle term, and it's going to be allowed because we have this positive y squared at the end. So we're having the case where we have x squared plus the 9 at the end. They're going to factor into relatively the same way. We're going to just use whatever those square terms are. So the first two pieces, we want to put an x times an x to give us the x squared. We're going to put the last terms as y times y to give us the y squared. If you then went through and you checked the outer, it's plus xy. The inner is plus xy. It gives us that middle term of plus 2xy. And because it's really just the same thing repeated, you can condense that as x plus y to the second power. When it's a minus sign, you're still going to do the same thing. You're just going to use minuses instead. So the first term still multiplied to x squared, but now negative y times negative y gives us negative y squared. If you check the outer, it's minus xy to give us that minus 2xy in the middle. Which again, this is the same thing multiplied by itself. It gives us x minus y to the second. So the main thing you're going to notice is this middle term is really going to tell us what the sign is going to be when we factor that out. Okay? So if we try this example, still doing my guess and check method, but it is one of our perfect squares. The very first term needs to multiply to k squared. So we'll do a k and a k. My last term needs to multiply to positive 9. But because I have a negative in the middle, it's a good indication I'm going to use a negative times a negative. And since 9 is a perfect square, we'll try negative 3 times negative 3. If we go ahead and look at the outer term, that's negative 3k. The inner term is negative 3k. It indeed adds up to the negative 6k that we want. So that is the correct factoring, and we can simplify just how we write this as k minus 3 to the second. So let's try some more. Again, got perfect squares for this next one. We need the first term to multiply to 4z, so let's try 2z and 2z. We need the last term to multiply to positive 1, and it's positive in the middle, so let's try plus 1 and plus 1. And now we'll check. The outer term gives us positive 2z. The inner term also gives us positive 2z. And adding those together gives us exactly the middle term that we want. So this factors really nicely into 2z plus 1 to the second power. Okay. For this next one, if I were just doing this like in my homework, I'm looking at this problem, it's kind of gross. There's really large numbers in front of both of them. I've got two variables in here. It's not great. And the other thing is 18 and 98 on their own are not perfect squares. So in this general approach, this is going to be the process that we want. I'm looking at this and I'm saying these numbers are way too large to run through combinations. So instead, what I'm going to do is I'm going to see, is there something I can take out? And the very first thing I notice is they're all even numbers. So let's at least take out a 2. Maybe I can take out more, but I can definitely take out a 2. And in doing so, 98 divided by 2 is 49, which is nice. 84 divided by 2 is 42. And then 18 divided by 2 is 9. So in taking out that single number, these first and last numbers are perfect squares, which is great. So I'm going to use that to my advantage, and I'm going to make my first guess those perfect squares. So to get 49m squared, we can do 7m and 7m. To get to 9n squared, we can do 3n and 3n. And I'm going to make it positive because the middle term is positive. Okay. So this is my good guess. Let's check. The outer term gives us 21mn. The inner term also gives us 21mn. And that indeed adds up to the positive 42mn that we want. So this factoring works. And then again, because it's the same thing repeated, I can just say it's that factor to the second power, and that 2 is out front. Now let's try our other special example, which is going to be perfect cubes. So this one should stand out from the others, that you need to go through this process because you're going to have third powers. And this is the only time we're going to have this formula pop up. So they're honestly identical formulas, except for the signs are going to change. And the way I like to memorize the signs is using a phrase SOAP. So S-O and then A-P. So the S stands for, you start with the same sign. So we have positive, starts positive, negative, starts negative. And then the O stands for the opposite sign. So you go positive, the opposite sign is negative, negative, opposite is positive. And then the last sign is always positive. Okay. Otherwise, the formulas are identical. So you have something cubed. You're going to put that something in the first spot. The next thing is still something cubed. You put that something in the next spot. Okay. For the first term of this piece that has 3, you're going to put the first term squared, and you're going to put the last term squared in the last spot. So it still follows a nice pattern of just that thing squared. And in the middle, you just do x times y, so whatever the thing being cubed is on each piece. So let's look at an example. We're going to start nice with 7 cubed plus 27, which z cubed you leave alone, but 27 you can write as 3 squared. So in this formula, my x is going to be z, my y is going to be 3. So what I'm going to do is I'm going to start by setting up my signs. And I'm going to use SOAP, so the same sign, the opposite sign, and then always positive. In my first piece, I just put z, because that's the thing being cubed. In my second piece, I put 3, because I'm doing 3 cubed. And now in this front piece, I'm going to take z squared. In the last piece, I take 3 squared. And in the middle, I do the product of 3 and z. So we have 3z. Okay. So to just clean this up, because we do have a little bit of algebra to do, that's z squared minus 3z plus 9. Okay. So this is my fully factored form. We can go ahead and check that this is the correct thing. We're going to kind of do a similar foiling process. So I'm going to show you how to actually multiply these out. So we want to take z plus 3 and times it by z squared minus 3z plus 9. In our foiling process, we're taking that first term, it's going to be multiplied by the other 2 pieces. So to think of foiling x plus 1 times x minus 4, you're going to do the first terms together, and then you're also going to do the outer. So the x is coming in contact with the other 2 pieces. And same thing here, the 1 is going to come in contact with these other 2 pieces. We're just going to apply that same process. I'm going to take z, and I'm going to distribute it to all 3 pieces. So z times z squared gives us z to the 3rd. Negative 3z times z gives us negative 3z squared. and then we have a 9z from that last piece. Then we're going to do the same thing with the 3. It's going to come in contact with all 3 other pieces. And I'm going to group them alike. So I'm really going to write this on the next line. So 3 times z squared gives us positive 3z squared. 3 and negative 3z is negative 9z. Positive 3 and positive 9 gives us positive 27. So if we add these together, the z squareds cancel and the z's cancel. And this condenses exactly to what we want, which is z to the 3rd plus 27. So this is really just a formulaic process, unfortunately. There are those key differences that you can remember, and there's nice patterns to this, but you are going to be using a formula to factor. So let's just try a couple more. We're going to start next with 8z, or 8x should be to the 3rd minus 125. And so the thing we have to figure out is what is being raised to the 3rd power on each of these. The second one is a little bit easier. So 125 is really 5 to the 3rd power. We know we definitely have an x to the 3rd power. And the number that's going to be raised is really 2 to the 3rd. So 8 is 2 times 2 times 2. So that front piece I can write as 2x to the 3rd and then minus 5 to the 3rd. So setting up our formula, we do the same sign, the opposite, and then always positive. In my first piece, I just get that 2x. In the second piece, I just get the 5. The front piece here is 2x, and we're taking that to the second. And the last is 5 to the 2nd. In the middle, we multiply the 2. So we get 2x times 5 in the middle. And then it's just a bit of algebra. That's 2x minus 5. This front piece, you distribute that 2, so it'd be 2 squared or 4. Then we get plus 10x plus 25. And again, you could multiply this out to verify that you put all the pieces in the formula correctly, but that is correct. For this next one, unfortunately, just looking at this, 3 is not a perfect square, and 192, I can't think of anything off the top of my head. So since they're not perfect squares, but they have that, or not perfect cubes, since they're not perfect cubes, but they have that x to the 3rd power, probably an indication that I need to take something out. So if you try doing 192 divided by 3, you can actually factor that out. It will leave you with 64. Okay. So this 3 is just going to stay out front. And then 64 is a perfect cube. It's 4 to the 3rd power. So we go ahead and set up our parentheses. We've got the same sign, the opposite, always positive. We're taking x to the 3rd and 4 to the 3rd. So our front spots are x and x squared. Our last spots are 4 and 4 squared. And then that middle is we do 4 times x. And so cleaning that up, we have 3 times x plus 4, x squared minus 4x, and then plus 16 at the end. So really, that's our main methods. Let's just do a few more examples where we do want to factor as much as possible, and we're going to jumbo everything together. So we have to identify which technique do I have to use, and can I even use one of these special formulas. So let's start with 9y squared plus 6z plus z squared. So looking at that, 9 is great. That's a perfect square. And then I have a 1 out front here that is also a perfect square. So I'm just going to jump into trying stuff to factor this out. And my first guess, because of the 9, is I'm going to do a 3 and a 3. And they both need a y with it. So those multiply to 3y squared. And then I'm going to try to make my last terms multiply to z. And the way we can do that is with a plus z and a plus z. So this is a great first initial guess. Let's go ahead and check that I get the right middle term. That's 3yz. And that is also 3yz. Those add together and give us 6yz. So indeed, that is the right factoring, and we can now just write this as 3y plus z squared. Okay. For this next one, thing I'm going to recognize is there is a cube here. So I've got to use one of my cube formulas instead. And again, I'm going to write that as 2x to the third power, and then 1 to the third power. So setting up our signs, we have the same, the opposite, and always positive. Our front pieces is going to be 2x, and then 2x squared. The last piece is 1 and 1 squared. And then our middle term is we do 2x times 1. So multiplying out the things we need to, 2x squared is 4x squared minus 2x, and then luckily 1 squared is just 1. Let's try 2 more. We've got a to the 4th minus 625 as our first one. And we don't have a formula for a 4th power, but however, a to the 4th we can write as something nice. So I can think of that as a squared times a squared. 625 is a very large number. So you could try a bunch of combinations to make this last term. You could do 625 and -1 or vice versa. 625 is definitely divisible by 5. You could try those as well. But here's where this pattern recognition comes into play. I have no middle term. So it's probably going to be the same thing in each spot because we put the same thing in this front spot. So really 625 is 25 times 25. So I'm going to make 1 positive and 1 negative. And go ahead and check. The outer term gives us -25a squared. The inner term gives us positive 25a squared. So the outer and inner cancel just like we want and leave us with nothing. So this is our correct factoring. However, not fully done. So this one I can't touch. Again, you could try to set it up, but because it's that plus 25, I'm never going to make my middle terms cancel. But over here, I do have something that is a perfect square. So again, I've got the minus. Let's try putting an A and an A. 25 is 5 times 5. We make 1 positive and 1 negative. And we're checking, is this the correct factoring for just that second piece? If you look at the outer, it's -5a. The inner is positive 5a. Indeed, those cancel and just leave us with no middle term. So this is as far as we can possibly factor it. For this last one, 20k squared plus 47k plus 24, 20 is definitely not a perfect square. Neither is 24. And I don't even have a number that will divide nicely into anything. So 47 isn't even. I can't take out a 2. 47 isn't really, it's only divisible by itself in 1. So this is an indication I just need to try my guess and check method. So let's go ahead and plug in some options and see if it works. So one thing I could do to get to 20k squared, I could do 10k and 2k. That definitely makes my first term work out. To get to 24, we could do 12 and 2. And so we'll check. The outer term here gives us positive 20k. The inner term gives us 24k. And unfortunately, that only adds up to 44k, which is not my right middle term. So that does not work out. So let's try something else. Another way we can multiply to 20 is 4k and 5k. Another way we can multiply to positive 24 is 3 and 8. And now let's see. If we multiply these two together, it gives us positive 32k. The inner gives us positive 15k. And if you add those up, it does indeed give us 47k. So this is our correct factoring. So when you're going through problems, you really want to try to pick up on these patterns. Pick up, do I have perfect squares at the front and end? Do I have a third degree power? That's really going to tell you what your good guess is going to be or whether you need to go into your formula. So our next section is really just going to be about how do I factor in general when I throw problems together? What approach do I use? And so we'll get more practice with that in our later section.